Yeah, so today we'll cover introduction to deep learning, the main basics and the main intuitions, the main concepts. And if you're wondering, like, who am I to talk to you about this if I'm not a PhD? So I'm a master's, but with a long background of experience in different R&D stuff and have some research publications. So I think I'm good enough and should be fine. So what is deep learning? Basically, you have some mapping from your input data to your output data. Yeah, given some x, you return fx, which is equal to y. And deep learning or deep neural networks, they try to approximate this y. Given some input data, they return some output which should be as close to y as possible. That's the main idea of deep learning, what they do. And the same concept can be written in terms of tasks, in terms of several tasks. For example, you have an image of a dog and a cat, and you want to put a box on a cat to show where cat is located on the image, or where is dog located on the image. Or you have a text in English and you want to get a text in French. Or maybe you have audio and you want to get textual transcription of this audio. Or maybe you have some textual description and you want to generate an image. All of this is the same concept of approximating some mapping F. Also, neural networks can play games or can generate some biological stuff, which I do not understand how it works, but probably some biologists within you, if there are any, understand it better. So the last one is basically using graph neural networks. So all of this is possible via deep learning. And one remark here is that you should think about tasks, not about domains. You should not think, oh, I want to do NLP, so I won't study audio, or I won't study computer vision, which is basically images. Why? Because in terms of a overall flow, let's say, everything is the same. You have some neural network, you give it some input, which is like a vector or matrix, and you return some output, which is also a vector or matrix. You do not care what exactly this matrix means. At least your deep neural network doesn't care about it. So the flow, like the pipeline, how your model operates, is the same for every domain. For example, if you want to do a classification of cats and dogs, you just put an image of a cat or a dog as input, and your model returns class 1, let's say cat, and class 2, let's say dog. But if you do some biology and you want to understand whether you have a normal plant or a plant with a disease, that's basically the same thing. Given an input, which is an image of a plant, you return a class, which is either plant is normal or the plant has like disease number 1 or disease number 2 or disease number n. Or maybe you do some text classification, like what topic this text is about. That's also the same thing. Or let's say you have audio sequence and you want to generate a continuation of this audio. Like you have first 2 bars and you want to generate second 2 bars. Or you have a time series like weather for this week and you want to understand what will be the weather for the next week. Or you have your favorite LLM like Gemini or ChatGPT, and you give your text and it generates some output based on your text. Basically, this is the same idea of after regressive modeling. Given some input sequence, you want to generate its continuation. Or more formally, given sequence x0, etc., xn minus 1, you generate xn. That's it. Or generation via diffusion. Given some noise, you generate image or you generate audio. It doesn't matter in terms of how diffusion works, whether you are working with audio or with images. So important thing to understand is that you should learn general concepts because they're identical for different domains. And then you can use knowledge from one domain and transfer it to another domain to maybe improve it somehow. and even get a paper. So there are a lot of papers, for example, in audio that just take ideas from text and from images, implement them in audio, and this is your new publication with a lot of citations. Of course, if you're a domain expert, you can incorporate some domain-specific knowledge, and this would improve the quality of your model even further. But it's not necessary to like take a specific course about, for example, deep learning for biology. You can take general course about deep learning for, let's say, images, and then you can do it easily in biology. You do not need a special course for that. You just read 1-2 papers, and that's all. You're an expert in deep learning for biology after it. Okay, any questions? No. Okay, so let's talk about deep neural networks. Given X, we return deep neural networks at this point X. That's easy. And deep neural network X tries to approximate some Y. The process of changing our neural network in such a way that it approximates Y as good as possible is called training. So we try to improve our model to get better approximation. But before we explain how training works, one useful remark is the difference between deep and machine learning. You probably heard like the term machine learning and the deep learning. What's the difference? Deep learning or neural networks, which can be seen as computational graph, as we will discuss later, can do everything on their own, meaning that you can pass raw data, and if there is a large enough amount of data and you have enough computational power, they can learn everything on their own. You do not need to care about specific features to extract something from your data yourself. While machine learning are much simpler algorithms, which sometimes are based on the same idea as deep learning, sometimes they are based on slightly different idea, but they are simple and they are relatively easier to interpret. So there is some theory behind them indicating how they work and how to understand their decision process. But they usually require handcrafted features, meaning that you cannot take like your raw data, your raw text, and just pass it to your machine learning algorithm. It probably won't work. At first, you need to pre-process your data somehow, extract some features, like let's say you have like time series with temperature. You cannot just pass temperature as is. You need to calculate like average, STD, something like this, and use average and STD as your features, or maybe something more clever. Of course, when you use deep learning, you can also use handcrafted features, as this probably would help. But in general, deep learning models are cool enough to do everything on their own. Any question? No. Good. So returning back to the training pipeline. Training a deep neural network is an iterative process where each step we try to improve our approximation. Given the total number of iterations, the training step, one iteration, consists of 3 steps. First one is obtaining our data for this iteration. Second step is calculating loss, which basically says how well we approximate our mapping F. And backward step, which updates our model and makes it a better approximator of a mapping F. Let's look at this figure here. So again, we have input data, we have our model, and it returns model output. We know that given this input data, the desired output, also known as ground truth, we know what the output should be, and we can compare model output with the desired output. To do so, we calculate so-called loss, like error function or loss function. These are the synonyms, which basically a similarity measure between desired output and model output. And we want this loss to be as small as possible, meaning that 2 objects, 2 outputs are as close as possible, as similar as possible, and basically meaning that we approximate our F as well as possible. And backward step takes this loss and calculates stuff from a calculus class, which is called gradient. We'll talk about it a bit later, and uses this gradient to update your model to make it a better approximator. Is everything clear? Yeah?
I'm not sure if it's different between what I already know. Not so work with labeled data. We already know what we want to.
Yeah, for now, let's always assume that we have a labeled data, meaning that for each input data, we always know what is the ground truth, what is the desired output. Next week, we'll cover some cases where you, for example, have only input data. Yeah, I guess I have a slide about this. Yeah, basically this slide. That, yeah, if you know ground truth, the task is called supervised. There are like self-supervised tasks, unsupervised tasks, semi-supervised tasks. But the main one that most often is used is called supervised task is when you know what is the desired output for each input. And let's assume that we only have this case for now. So first step that we had in our training pipeline was getting data. To do so, we need a data set, which is a set of data that you use to train or to evaluate your model. And it is very important to split your data into several partitions, meaning that you have pairs of X and Y, and you split it into train partition, which you use to train your model, and testing partition to evaluate your model. Why do we need these splits? So first of all, there is an infinite number of possible pairs of X and Y for any task. For example, you cannot take a photograph of every dog that exists in the world, or you cannot take it in every possible place. Yeah, you cannot take a dog which is located in Turkey here at EPFL on the inside with the mountains background. Yeah, so you observe only some part of the data, and you can save only some part of existing data on your computer because you have a finite disk space and drive space. So let's look at this example here. Let's say that our mapping F is this gray line here. And what we actually observe is these orange dots. Yeah, we know that for this X, the observations that we got, this ground truth Y, is this orange dot here. And for this orange dot here. But maybe if we did some different, if we had some different data set, we would have something on the right where we have some dots here, which were not present on the figure on the left. So when you get your data set, you do not know whether you're on the right, whether you're on the left, and you should create a deep neural network that works well both in the case on the left and in the case in the right. You saw that some orange dots were not located on the gray line. This is because even if the inputs are fixed, the noise may change the given ground truth a bit. Yeah, so Y that you observe is actually Y real plus some noise, which can be caused by many, many different things. For example, when you take a picture of something, your picture depends on like which camera you used, which sensor this camera has inside, like how dark was this time of like what was the time of the day when you took this photo, etc. And this could alternate your picture a bit. And this is not only about pictures, this is about any data you have. Like in physics, you measure with some devices. These devices are not ideal. They have some small errors that you cannot fix. Yeah, so you have a data set like this orange dots. And you can train different models using this input data. You can maybe train a model like this, which looks like a line, and we see that it's completely awful. Or we could train something on the right, which looks good, but only if we consider these orange dots. Yeah, this line almost perfectly captures all orange dots here. But when it comes to this position here, we see that orange line is completely different from the actual ground truth gray line. So the situation on the left, where our model is bad even on training data, is called underfitting. And another way of interpreting this is when we change one dot, like this orange dot, we move it a bit to the left, our model wouldn't change a lot because it doesn't actually care about any specific individual dot. While on the right, if we change, let's say, this dot and put it a bit to the right, our model would change significantly. Probably this peak will be somewhere here, yeah, instead of here. Or maybe the behavior of the model will be completely different. This is called overfitting. So we perform well on the training data, but if we change something, everything changes. And also, we are not actually approximating our gray model well enough because of these points here. So basically, splits allow you to answer the question how well my model really performed. Because you cannot use training data to answer this question, yeah? If we use training data, we would say that model on the right is perfect. Yeah, it captures almost all orange dots perfectly. While in reality, it's completely awful because it's not approximating a gray line here well enough. So this is because your model knows this data. It knows what is the desired y for this x. And it's some sort of cheating, yeah? When you know what should be the output, you, of course, perform well on this output, on this input. But when you are getting new input, you do not know what to do because you overfitted, overlearned, let's say, on these training elements. So performance assessment should be done on unseen data, like this data in green. If we had this data in green, which we call test data, we would notice that this orange model is completely awful because the distance between the predicted output, which is orange, and the actual ground truth is huge. Yeah, and we will get like this huge loss, huge error, and we would know that this orange model is awful. While we could maybe train something in between, we should be this black line, and it would approximate our gray line almost perfectly. It's maybe not so good in terms of capturing orange data. Yeah, we see some distance here, but it's much better in terms of green data, and it's much better in terms of approximating this function f. And without test data, you wouldn't know it. Any questions? No? Yeah, people on Zoom, I don't know if you asked anything by your voice. It's better to write in the chat in any case. Okay. Yeah. So in reality, you may have 3 splits if your data allows. The first one, as we said, is train split, which you use to train your model. The second one is called validation, or sometimes also called development set, which you use to, which is first of all unseen, so you do not train on it, but you use it to choose the best model within the set of trained models. For example, you trained like model number 1, you train the same model, but change some parameters, like you modified your algorithm a bit. Now you need to understand whether you need to use model number 1 in production or model number 2 in production. For this, you use this validation set. And the test set, also known as the evaluation set, is the one which you do not use at all except for measuring the final performance. So you cannot make any choices using this test data set. Let's say that validation is something you have in your company where you can assess your performance, and test set are real users once you already publish your model in production, And now you're getting some feedback from real users, and you cannot like adapt for them in advance. You get these test metrics only once you already put something in production. So to choose a model, you use validation set, and to actually avoid any cheating, you calculate your metrics on test set where you do not make any chances on. Any questions? No. Good. But because you have unseen data, there are some disadvantages. Because your model could overfit on the training data, as we said, and it probably performs as this orange line and not as the actual gray line. So the performance on the unseen data can be much worse than on training data. To mitigate this problem, there are several generalization techniques. One of them is, for example, using larger training data set, if your data allows. Or another technique is called data augmentation. Basically, you modify your input a bit so the output stays the same, but the input is slightly different. Like in terms of mass, the distribution of your data is a bit shifted, while Y stays the same. For example, we have a picture of a dog and we want to classify whether this is a dog or cat. We know as humans that this is dog here. But we also know that this is dog given only a part of this image here on the slice. Or even if we erase the face of the dog, we still understand that this is a dog. So we expect our neural network to also understand that this is a dog. Yeah, there are different versions of what we can do. And in all these cases, we as humans understand that this is a dog. So it would be great if our neural network would also understand that this is a dog. And we artificially increase the amount of our data, which therefore improves the generalization of our model and performs better on unseen data. Any questions here? Yeah.
For the, I think you mentioned that for the validation data set, it's always unseen data, right?
Yes.
And this data is never staying in the training data.
Yes.
And I remember there's some method like one-shot learning and the few-shot learning and zero-shot learning.
Yeah.
Because I think the zero-shot learning is something that is specific for the totally unseen the validation data set.
So the concepts you're talking, which are zero-shot learning, few-shot learning, and all this stuff is a bit different. It's more about LLMs actually and large models, and well, yeah, and it works as follows. Let's say you trained on a number of different tasks. Your model can do classification, can do, let's say, generation, can do detection. And now you give completely new task, let's say machine translation. And for some reason, your model can actually do machine translation because it could use so large amount, it's have seen so large amount of data during training that it actually internally somehow learned how to do some other tasks too. So when you talk about zero-shot, few-shot, one-shot, you change the task, while validation set, test set, etc., is within the same task. Yeah, few-shot is when you give some examples. For example, you give several examples for the model on how to translate from English to French, and this actually improves your LLM performance even further. I'm not sure if you're going to talk about this during the LLM lecture next week, but thank you for the question. There are some questions on Zoom. Can synthetic data be the cause of hallucinations? I would say possibly yes. So if you have real data, that's always better than doing any type of augmentation. The problem is that for many tasks, especially for niche ones, like when you do some biological stuff, you probably cannot collect a huge amount of data because it's time consuming, this is expensive, etc. So in these types of tasks, the only way for you to go is to generate something synthetically. But when we talk about LLMs, of course, we can use huge number of data from the internet, and we probably do not need any synthetic data at all. So in theory, yes, synthetic data can be cause of hallucinations, but for some tasks, that's the only thing we can do to actually improve the quality of our model. Yeah, so the second question is, I do not understand how modifying the same image is considered as data augmentation. So data augmentation basically means that you augment your data, like change it a bit to make the amount of your data larger. And so modifying the same image is considered as data augmentation by definition, let's say. But I guess the question was basically like why it helps. It helps because, let's say, all our images of dogs are looks like this. They like the dog is looking at us, and we are capturing like its face. But probably when I use your model, yeah, let's say, so this is a bottle is, let's say, a dog, yeah. So during training, for example, I always saw dog like this. But maybe when I put it in production, someone, like some kid, took a photo of a dog, but a dog is like this, it's rotated a bit somehow. And because your model never saw this kind of dog, which looks like a bit to the right, it wouldn't understand that this is actually a dog. It could hallucinate and say that this is a cat or something else. While if you used this sort of augmentation, which is rotate one, your model would be robust to this kind of transformation. It would know that if you changed the position of a dog a bit, it's still a dog. It doesn't change, like dog doesn't stop to being a dog because of some shift or because you have a noisier data like this JPEG compression thing, or because you took a photo like this instead of like this. One question, wouldn't data augmentation lead to overfitting on training data? It may, so you need to be careful. And for this reason, you always monitor performance on your validation on your test set while you're training, and you try different approaches, whether maybe like doing more augmentation, doing less augmentation, or not doing augmentation at all. So like data augmentation may help, but it doesn't necessarily help you all the time. How to decide what kind of augmentation is appropriate for the test data is just dependent on the data we have seen before. Like, yeah, so it's dependent on the domain knowledge. You, for example, know that dog doesn't change if you do it like this. So yeah, that's based on, that's where your domain knowledge could help. How would this work? Example, if we have a GPG dog versus PNG dog, the bias sequences are very different. Sure, we see the dog, but the bias the model would see would be totally different. So actually, when you work with the images, you do not load them as like GPG or PNG. You load them to a matrix with values between 0 and 255. So your input is always this kind of matrix with values between 0 and 255, and it wouldn't matter how this, what sort of compression you used for your image. Of course, like when you visualize it, it will be a bit worse when you use JPEG instead of like PNG, because PNG is lossless. But this would just alternate these values between 0 and 255 a bit. So, and your model would know what to do in this case. Well, when we do data augmentation, don't we change the input class? How is the model supposed to know how to classify it? So the idea of data augmentation is that you change input in a such way that ground truth doesn't change. Yeah, you know that this is a dog because you just rotated a photo. You do not want to alternate your input in a such way that the ground truth also changes. There are some advanced augmentation techniques where you actually, for example, mix dog and a cat, but you then also mix the ground truth classification too, classification label too. But we won't cover it, at least today, it will be too much. Is everything clear now? Yeah, nice. Yes. Okay, so we covered what is data, but what is a model? Model or deep neural network can be seen as a computational graph. So this is basically a stack of layers that return new output given the output of previous layers or the input data. For example, we have input data and our layer 1 returns some output, layer 2 takes some output and returns output to layer 3 and also to layer 4. Layer 3 returns output to layer 4 and layer 4 takes input from layer 3 and from layer 2 and returns the final output. And actually, you can create this computational flow in any way you want it to be. For example, you want to create a branch where some part of the output from layer 1 comes to the first branch and some part comes to the second branch. And then you combine these branches together in the layer 4, for example. And maybe layer 4 also takes some part from here. You basically do not, like your deep neural network and the way how you train it doesn't actually care about the specific design, let's say, like of course it cares. I mean, you do not have restrictions on how you design it. So it's up to you based on some logical ideas to design it properly. But in general, the concept is that your deep neural network is just this computational graph. It's the input flows from input data to layers to intermediate outputs to the final output, which you compare with your desired output. Is it clear? Yeah. So, and one layer is basically some function, any function, that given input data and or the output of previous layers returns some new output. That's all. We will cover what types of functions usually used tomorrow and basically this whole week. But the overall concept is like this. Okay. Okay. Are CNNs also considered DNNs? Yeah, CNNs are deep neural networks where convolutional layers are used as this type of layers in blue here. We'll cover it tomorrow. Okay. Yeah. So now we go to the only mathematical thing that is going to be during this bootcamp, except for maybe diffusion next week. And if you do not understand it, it's okay. But it's important to get at least like some intuition about it. And I hope to make it as easy as possible for you to understand. So this is about how you actually update your model and make it a better approximator. So your neural network is a function which, given some input data and some parameters, also known as the weights that you actually update, return some output. And your goal is to make your deep neural network as well performer as possible, meaning that you want to find good parameter values that allow to predict the desired outputs for new inputs. And let's consider a small toy example here, which is basically you have like 2 points, 2 features, feature 1 and feature 2 as input, x1, x2, and 2 parameters, theta and b. And your deep neural network looks like this. It's x1 cosinus theta plus x2 sinus theta plus b, where theta and b are parameters that you will be updating to improve your model. We also call it optimizing your parameters. In terms of image, it looks like this. So you have these circles, which are your data points. And if they're in blue, this is, let's say, class number 0. And if they're in red, it's class number 1. And your deep neural network is this line in black. And we say that if the point is above this line, we believe that the model believes that the output is class number 1. And if the circle is below this line, it's class number 0. So ideally, we would want, via training or optimization, move this line from this position to something like this, which performs well on training data. Yeah, it separates these blue lines, blue dots from red dots, and also performs well on test data, which are these gray circles here, this one, and this one. Yeah, so you see that green one is probably much better than the black one, the original thing. And your training basically tries to understand how to change theta and b to go from here to here. Okay? Yeah.
What is the gray lines?
This line.
No, 3 vectors.
This.
3 lines.
This one. So these are just to highlight that we put a question mark here. It's not a vector. It's So these are our data, and to make it clearer for you that this is like unseen data, we put a question mark here just with an arrow. Yeah. So how it works again? How you optimize it? So you have your prediction f. And you compare it with 0.5 to say which class it is. So like it is class number 1 or class number 0. And this is your prediction. And to understand whether your model is good or bad, you use so-called metrics. You should separate in your mind the concept of metrics and the concept of loss functions or error functions. So what is a metric? Metric is any function that allows you to understand how well you can solve the task. For classification, this is simple. This is like how many times you guess the correct answer, how many times your model predicted answer is actually the same as the correct answer. And if your accuracy is 100%, this means that you predict correct answer all the time. If it's 0%, it means that you are always wrong. And of course, you want 100%. The problem with this type of metric is that you cannot use it to train your model because it's not differentiable. So you need something else, which we say is the loss function, which is also a measure of how well your model performs, but it's differentiable. Meaning that we'll be able to apply some calculus and calculate some gradients to update our model. So here it looks like this. We say in terms of, instead of either saying like using indicator function, which says 1 if y is equal to y hat and 0 otherwise, we use mean squared error, which is a squared difference between f prediction and y. And we can calculate gradient for this stuff, which is basically how our loss function changes when we slightly modify the values of our parameters. And the main idea of deep learning optimization is this update rule. So given theta and beta, theta and b from the previous step, we calculate the gradient and use this gradient with some coefficient, which is also known as a learning rate or step size, to go from these values to new updated values. Is this clear?
No.
Where are you lost?
in the loss function.
Is a loss function. So did you understand the difference between accuracy and the loss function? Did you understand what is accuracy?
Accuracy, yes.
So accuracy again says how many times you match the correct answer all the time. Then the problem with it is that you want to calculate these gradients, but you cannot do it for this accuracy function because it's not differentiable. So gradient doesn't exist for this function, let's say. So you want something else which theoretically does a similar thing, but it's not exactly accuracy. Maybe I should show it with the, I don't know, people on Zoom, will you see it? Probably will. Yeah, D is the number of elements in the data set. D is the data set. So where are people on Zoom and so you see here, yeah? Yeah, should be fine. Yeah, so let's say you have like objects like this, like zeros, and here we have ones.
Can you write a bit lower, please? Like this, the board is seen, but it's really need to be a bit lower, just a bit.
Okay. Here is okay, yeah?
Yeah, here is okay.
So let's say this is one. Yeah, so let's look at the segment between 0 and 1. And let's consider some input x, and for this x, you predicted fx, which is somewhere here. So this is your value fx. And basically, you say that if fx is closer to 0, then we believe that fx is 0. Like the predicted class is 0. Or if fx is closer to 1, the predicted class is 1. Okay? So the problem with accuracy is that you shift fx to the closest neighbor. Yeah, you shift it to here. And this is not differentiable. But instead, you can say, okay, let's calculate this difference here. And if x output for x should be 0, we want to make this distance as small as possible. And this is differentiable here. So now instead of directly saying that fx should be equal to 0, we say that fx should be as close to 0 as possible. And this is basically fx minus 0. Or in more general, this is fx minus y, where y here is equal to 0 and y here is equal to 1. Okay? Now we say, okay, we could probably, we do not care if we are on the right or if we are here on the left. Yeah, maybe fx could be here. So what we could do, we could say, let's use absolute value, fx minus y. But instead of having absolute value, we say we could use the square, and it's basically the same thing. And now, if we make this as small as possible, this would move fx as close as possible to the ground truth label, and then doing this sort of thresholding with 0.5, if we will, like, the fx which will be on the left part will be considered as 0, on the right part as 1, and our model will perform well. Is it clear now?
think yes. So accuracy would be more for discrete numbers. And
Yeah, accuracy is for discrete case, and it's not differentiable.
loss for continuous.
And a loss is to make it differentiable, to make it, to work with this continuous phi. So basically the thresholding happens here. Yeah, we go from fx to y hat. And we want something with fx without this thresholding to avoid this discrete case, which makes our function non-differentiable. Okay. Any other questions? Everything clear now? Yeah, people on Zoom. Yeah, so D is our data set, and absolute D is the number of elements in the data set. With the training, do we need to get most of classes conjuncted? What is conjuncted? I don't know. Sorry.
That's right.
Hmm?
That's right.
For the do we need? Yeah, so we hope to get as good. So yeah, we hope to get as good quality on training data too as possible, but we want to avoid overfitting, because otherwise we also training to match this noise and not the actual ground truth, not this gray line we saw at the beginning of the lecture. Does each model have a unique loss function, or can there be plenty and we just search for differentiable loss functions? Yeah, so the design of your loss function depends on the task you solve. For example, for classification, you could use the squared one, or you could use, as we said, the one with absolute value, or you can use the so-called cross entropy loss, which is with logarithm and something else. So there are plenty of different loss functions, and you choose the one which works better for your specific task and which is designed for your specific task. Yeah, if you're working with classification, you probably do not want to use losses which are for generation, let's say. But yeah, we search for any differentiable loss function. We can use the standard one for this specific type of task, or design a completely new one. Okay.
In that case, what I don't see now is how does the gradient become useful?
So gradient is the direction to which you should move your parameters to make the loss bigger as possible. But we use anti-gradient. We use minus here. So minus gradient is the direction to minimize your value. And we want loss function to be as small as possible to make this distance as small as possible, because we want this to be as similar as possible. So we want to get to the minima of our loss function. That's why we use anti-gradient, and that's why it's useful here. It's clear now?
Yeah, thanks, Peter.
Yes. People on Zoom? Yes. Yeah, so let's look at the visualization on how it works. Let me just stop it to explain. Yeah, so we have several plots here. So this one is the same as before. We have our circles, which are either positive or negative classes, or 1 and 0, or 1 and -1, as you wish. And our function, our deep neural network, is this line here, which basically splits your surface into two halves. Yeah, one above is for positive class, one below is for negative class. And when video plays, you see that this line changes. Yeah, your model is being optimized, and this line changes from what was bad to something which is actually quite good. And this plot shows your loss function on this training data, your loss value. yeah, you start with something very bad because you start with something random and your model doesn't approximate your y well enough at first, but then it goes down and it becomes better and better approximate. And this plot on the left is maybe a bit hard one for those who are not from computer science or math. This is like a loss surface where the color, again, is about the loss value. So yellow means loss is high, blue means loss is low, and you want to go from yellow to blue. And these black circles, ellipses, show the points where loss is the same. Yeah, so it's called like loss level. The value here and here on the same ellipse are the same. The loss values are the same. And you start from here and iteratively. You improve. You move to the direction of anti-gradient, and you go from this high loss position to this lower loss position. And here you see that it becomes a bit harder to go even lower because you're already very close to this minimal. There are some questions. I don't understand why isn't the gradient descent the line completely perpendicular to the level lines at the start. Oh, actually, it's perpendicular. No, it's not perpendicular. I guess it's called like, so. Here is the 90 degrees. Yeah, okay. So it's as expected. Should be fine. May you repeat the video, please? I already repeated. Is minimizing loss essentially the same as likelihood maximization? Could likelihood be used then instead? So likelihood maximization, or likelihood loss, is one type of losses that you could use. So likelihood optimization, maximization is basically the case when you use cross entropy loss. While here we use a mean squared error because it's simpler and easier to understand. But yeah, like likelihood could be used as one sort of losses, one type of losses. Using gradient descent, we found the local minimum, but how can we find the global minimum? The problem is that we do not know if you are in a global minima or in the local minima. And it's like, you do not know whether you are going to end up in the global minima or in the local minima. And that's an issue. And that's why sometimes you want to maybe use the next method we will cover that lets you go out of this local minima and find the actual global minima. But yeah, in case when your loss surface looks something like this, and if you are here, probably there is no way for you to go out and end up here. Like there might be some cases where you are able to do it, but in most cases you are stuck here and you can do nothing about it except for starting training again from a different position. Maybe here you started from here, yeah, and if you started from here, maybe you would end up here and it would be better. But you do not know in advance whether you're starting here or you're starting here. That's an issue. Even better Markov chain MC. It's about so loss function is not necessarily convex. As you see, it can be like this. And even here, you see that there is some thing here and something here. Yes, so some minima here and some minima here. And we are going here, but maybe you could go here if we started somewhere closer here. Yeah, we have a coding section today. Yes, there was a question about coding section. Yeah, so the problem with gradient is that it's very expensive if our data set is large. Imagine you have like 1 million images and you need to calculate your loss for these 1 million images. That's time consuming, first of all. And secondly, that's not exactly necessary. And thirdly, if you use your full gradient, no, I would say the third one a bit later because it won't be clear right now. So the idea is that we do not want to calculate the full gradient, it's too expensive. Let's calculate it only on a subset of data, which we call batch or mini batch. So we take some subset of specific size, let's say like 32 or 64 or like maybe 8 or 5 different images or 16 different images, and we calculate loss only using this part of our data. The loss function is the same. Yeah, we calculate loss for every point, but instead of calculating it for every point in the dataset, we calculate it for every point in the batch and take the average. And we use gradient only for these elements that we used only inside this batch, and use this gradient instead of the general one. Yeah, so we use this gradient and not this gradient. Yeah, so we take the gradient of the same function where there is b instead of d. Yeah. So we only need to compute b points per update instead of d, which allows to speed up our process significantly. And it's also noisy estimate of full gradient descent, full dataset gradient, which comes with a first, you can think about it as a disadvantage because it's noisy, it's not very great, but at the same time, it's better because you introduce some randomness, which allows you to go out of this local minima. Yeah, if you end up here, and the random thing may work well for you, and you just randomly jump here, and then you will be able to go down here. While for full gradient descent, you would always stuck here in this local minima, and you wouldn't be able to jump back here. So using stochastic gradient or mini batch gradient descent doesn't necessarily allow you to jump from here to here, but it would be more possible than using full gradient descent. And let's look at the visualization. Yeah, exactly the same thing, but you see that we are not going we are not having this 90-degree thing. We are moving a bit randomly, a bit to the left, or a bit to the right, and our loss on a mini batch can get lower, can get bigger. Our we need to stop it somewhere here. No, maybe here. Yeah, we see that maybe even loss on the full data set can sometimes get a bit bigger than it should be. So it's not monotonic now. Yeah, you can for some iterations, your loss on the whole data set may become larger, but on average, it becomes smaller every step you take. Yeah. So, and your loss for a specific batch also is a bit noisy, and that's why you see this blue line. But on average, you're doing pretty well, and you end up at the same local minimum. No, not on the same exactly, but in this area around local minimum. Is the stochastic method equivalent to condensing point clouds and taking only of them to then use the gradient? I didn't understand the question fully, but yeah, you take only a random subset of your points and calculate gradient only on these points. Data B changing for every iteration. Yeah, for each iteration, you take your new subset of the same size. Yeah, you can see it here in the video. Yeah, mini batch is in black. And if you go to the beginning, yeah, we start with like these elements. then they change to these elements, to these elements, to these elements, etc. So you take different subset of data every time, but the same size of data. How do we know that our stochastic gradient descent is sufficiently random so that we can maybe escape a local minimum to reach a global one? So that's a mathematically heavy question. I would say you need to go more into optimization class to answer it, and actually to answer why stochastic gradient descent works and can achieve minimal pretty well. For now, let's first believe that it works good enough and can achieve good enough performance. And secondly, in terms of intuition, why you can escape the local minima, again, because of some randomness, maybe for some mini batch, you will jump out of this local minimum. It's not 100% true that you will always do this, but because there is some randomness, because this is a stochastic thing, not a deterministic thing, there is a chance that you will jump out. But maybe you won't. But at least there is a chance, which didn't exist in the full gradient descent case. This randomness made us do much more steps. Is it still efficient? So first of all, each of the steps is much cheaper than full gradient descent step. So yes, with full gradient descent, for some simple task like this one, you may use smaller number of iterations to achieve the same performance. The problem is that for many tasks, first of all, you cannot calculate full gradient descent. And secondly, calculating it will be much slower than doing several iterations of a small one. So let's say, like, for some tasks, maybe calculating full gradient descent will take 10 seconds, while calculating stochastic gradient descent will take 1 second. Then you can do 10 iterations of stochastic gradient descent, while you did only 1 iteration of your full gradient descent. So yes, you did more steps, but you did it within the same time period. And your final, you can end up training before you could be able to finish it with the full gradient descent. We update we update all parameters. So the question is, do we update only B parameters? No. So this B is only about how many elements we take for our loss calculation. Yeah. So we still have theta and B, and for all theta and B, we calculate this difference. But for x1 and x2, we only take the subset of B. There should be B, it's missing. Yeah, like here. So we take x1, x2, and y from B, but we always have the same theta and B, and we always update it no matter if we use full gradient descent or stochastic gradient descent. It's closed.
Okay.
Yeah, sorry. So to choose B, that's another question. So you choose the size of B, and then you take a random subset B. So if you know the size, you just randomly, like let's say uniformly, take some elements, B elements from D. In terms of how to choose batch size, it depends on the task. So first of all, and on your hardware, because you have like your laptop or your server, your computer, and you cannot have very huge batch size if you are limited in terms of memory. Yeah, because to process, like, let's say 1,000 images, you need, let's say, 100 gigabytes of memory, but you have only 10 gigabytes of memory. That means that you can only allow yourself a batch size of 100 and not 1,000, because you are just limited in memory. So one thing is you can increase the batch size until your hardware allows you to do so. So if the maximum batch size you can use is 100, you use 100. If it's 32, you use 32. So that's like a simple rule of thumb, which you can use to choose your batch size. However, sometimes people prefer to use smaller batch sizes just to make more updates. Because as I said, the larger is your batch size, the longer it takes for you to calculate one step. And maybe you want to do more steps instead of one large step with a larger batch. So the good thing to do will be to maybe, first of all, try your maximum one. And secondly, to try different ones to see which one works better for you. And one last thing, which is maybe more advanced, there is a thing called effective batch size, which means that after certain number, making the batch size bigger doesn't make any difference for you. Okay. Okay. We still find the vector of gradients for all parameters, but in our sum sigma using only parameters from batch. So I guess you misunderstand the concept of what is parameters and what is input. So your parameters are for your model. This is a theta and b. Your batch and your data is only this x and y. You do not update x and y. These are given. You update theta and b. So you use only data from the batch to update your theta and b. That's true. But you update all your parameters. And the second question assumes that we have input image like batch size, channels, height, width. We'll go gradient descent for our image from batch, so batch size is b. Yeah, batch size is b in this situation. B, I mean, absolute b. Yeah. Clear for everyone? Yeah. So simple example. Yeah, this is our computational graph. Yeah, the same functions that we had, but now as this input, intermediate layer, intermediate output thing. Yeah, we have our theta, we have our b, we have our x1, x2, and each layer is some simple operation like taking cosinus, taking sinus, taking multiplication, summation, addition, subtraction, or etc. So that's a simple thing, and we calculate intermediate outputs, which are like z1 here, z2 here. So z1 is like cosinus theta, z2 is sinus theta, z3, z4, etc. So we calculate all this intermediate stuff. And this is our loss that we compared this output with this y. Now we want to update it. So we want to calculate the gradient, but we want to make our life as easy as possible. So we use a so-called chain rule and the whole algorithm is called backpropagation. This is the main algorithm in deep learning theory, let's say, which says how you compute your gradient for your huge neural network using only intermediate layers and intermediate gradients. So what's happening? You start here and you say your gradient is 1, like all ones, and your like the last thing before your output was this z9. So let's calculate gradient only for z9. It's this thing which using which basically this thing, and we know that for z9 squared the gradient is 2z9 squared, 2z9, sorry. Then we want to calculate delta 8. So delta 8 using chain rule is basically delta L divided by delta z9. Delta z9 divided by delta Z8. So like you can see it as if you add the same thing to numerator and discriminator, they kill each other and nothing changes. Yeah, so you can like cross this out here and here, and you get the same thing as on the left. But you actually calculated this before here. So you can pass it inside here. We calculate like delta 9. And because because Z9 is subtraction, we here have this thing as 1 also. So after multiplying 1 by delta 9, we get delta 9, and delta 8 is equal to delta 9. And we do the same thing for all the layers, like we calculated delta 9, then we calculated delta 8, then we calculated delta 7, then we calculated delta 6, delta 5, delta 3, delta 4, delta 2, delta 1. And finally, we get, it's not written here. Finally, we get one delta which corresponds to B and one delta which corresponds to theta to actually update our parameters to calculate this delta L divided by delta theta and delta L divided by delta B. Like most people would kill me because I say divided, it's not division, but you understood the idea. Yeah? Clear or too hard?
So basically we need just 2 parameters and the others are like 2 deltas and 2 z vectors, and the others we just use that for calculating them, or?
Yeah, we use them as intermediate steps because it's easier for us to calculate delta 9 instead of directly calculating this thing. Yeah, we calculate intermediate things, then we update our B and delta, and we do not care about these intermediate things anymore.
Okay, got it. So we just use 2 vectors for gradient descent, and the others just for calculating these 2 vectors for gradient descent.
Yes.
Oh,
yes.
Okay, got it.
Yeah. So the whole idea of backpropagation is to propagate your loss from your final layer to your first layer. Yeah, you propagate it by doing one step here, one step here, one step here, like the flow is going backwards. That's why it's called backpropagation. And basically you have like a forward step, which is this blue line. You calculate your output, you calculate your loss, and your backward step, where you update your model by calculating these gradients in an opposite direction. I forgot to say that there is forward backward, but now I guess it's clear. Yeah? Good? Good. So probably you thought that this is too mathematically hard or too complicated, and it's hard to do it. So the good thing is that we do not have to do it now at all. Like we do not care about, we just know how it works. But in terms of coding, we do not care because PyTorch will do everything for us. And we say, thank PyTorch. So what's happening? Yeah, we have our theta, we have our B. We define them. We'll talk about this in the coding part. We define our input data. We calculate our loss as before, and we just call loss.backward. And loss.backward will calculate gradients for this theta and B itself automatically. How it works? So PyTorch inside creates this computational graph. It knows all these Z values. And given these Z values and these sort of operations that were used, like sum or minus or multiplication, it knows what should be the gradient and applies this chain rule automatically. And this allows it to automatically calculate the gradient, and now you do not care how to do it by your hands, I mean. Is everything clear until now? Good. So one last thing in terms of theory for today is how to choose the learning rate. Remember that we have our gradient, and we added this eta thing, eta coefficient before the gradient, which basically says like to make a larger step or a smaller step. So choosing this coefficient is very important, and it might be the most important thing to choose for your model. How it works and why it's important. So let's have a different example of a function like this one. And we have the same plot where blue means like this is our optimal thing. Yellow means that the loss is high. We do not like yellow. And we start from this position here. So if we choose small learning rate or small step size, we will be able to easily avoid overfitting on the noise inside our data, but it will be very hard to move if we are already close to the local minima. Yeah. So local minima is here, but the loss here is not too far away. And with small learning rate, it's very hard for our model to get here fast enough. So we make very slow progress along flatter directions. Yeah, so this is our loss. If we use high learning rate, we move much faster. Yeah, so we do not need like several steps to go from here to here. We directly do it in one step. The problem is that we become our training becomes very noisy, and we are jumping like here, 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 here. And at the end, when we are close to this minima, yeah, we can just jump here, then jump here again, then jump here again, then jump here again, and we never people on Zoom, can you hear us? Because it shows preparing meeting.
Yeah, we do hear you.
And I lost chat. I don't know. Strange. Oh, well. Yeah, sorry. Yeah, so having too high learning rate is also bad because you jump all the time and you cannot get away from this jumping. You are not actually getting here to the local minimum. So it would be better to use something in between, something like medium, where you are able to make decent progress along the flat direction, but also it's not too noisy. And you see that you are able to achieve much lower learning loss than before, and much faster than when you had a small learning rate. However, the best thing to do is to learn so-called learning rate schedules. So you change your learning rate with each iteration. You start with something big to make progress fast at the beginning, and then you make it smaller after several steps to avoid being too noisy when you are already close to the minimum. Yeah, you start somewhere here, and then you decrease it, and your learning rate is almost zero at the end. And this allows you to jump fast at the beginning, and then closer to the end, you make your steps smaller, 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 and you end up in the minimum. Is it clear? Good. Yeah, so this gradient descent, stochastic gradient descent, etc. These are all variants of gradient descent. And the one which people use in practice today is called Adam or Adam W. Adam W is a bit different from Adam, but the guy from machine learning optimization laboratory said it's better to use Adam W now for some theoretical reasons. So let's say that Adam W is the best, but most often you will see either Adam W or vanilla Adam, and it adds some tricks to your standard stochastic gradient descent, such as momentum, where you use some knowledge, use your current gradient and some information from previous steps. Because, like, what is the idea? The idea is that remember, you had like very noisy jumps, but if you smooth them using this weighted average, you would go something like this and make it less noisy. So that's the idea of this momentum thing. And that's especially useful for large batch sizes, but doesn't hurt when you have a small batch size. There is also a thing like gradient normalization, which is a second line, similar idea, which helps for certain network architectures and also doesn't hurt in any case. And weight decay. So when you learn what about weight decay in a standard deep learning course, they would say that this is like a regularization, which helps you to avoid overfitting. But again, this guy, Ali from Ali, not Ali, I forgot his name, but so I'm sorry for that. But yeah, so from machine learning optimization laboratory, he said that weight decay is not about regularization; it's a bit different thing, and this is a common mistake to believe that this is about regularization. So it's just something that makes your training more effective in special cases, and you can skip this parameter. You can use like some default one, play with it, and it may help your performance. Yeah. So recommendation is to use NMW unless you have a very good reason not to use it. And in practice, you try running your algorithm with different learning rates, like a large one or a small one. Yeah, large one or small one. And to find the one which works better for your tasks, you something like maybe 10 minus like 3, 10 minus 1, something like this. Yeah, so choice of the learning rate can strongly affect your performance. And there is no magic value that works for all. Yeah, there is a meme in Twitter saying that you should always use 3e minus 4. And in many papers, you see 3e minus 4 just because of this meme. Because people don't care and they just use this one. But probably if they would change it to something like, I don't know, 1e minus 4 or 1e minus 3, it would be better for that task. So in practice, people usually try like something like this meme, 3e minus 4, 1e minus 4, 1e minus 3, and that's all. Some better researchers would try more if they have enough computational power and time. What is GT, MT? So GT is our gradient on a iteration T. MT is our momentum calculated as following. VT is our normalization thing calculated as follows. And PT is the thing we actually use to update our weights. So it will be like weight new is equal weight old minus learning rate multiplied by PT. No, PT is our weight here. Sorry. PT is our parameters. That's why it's P. Sorry. So this is our final gradient update. And this is our weights on the previous iteration. Yeah, and in practice, it's also a good idea to use so-called warm-up, where you start with a very small learning rate, then increase it, and then you go down. Why so? Because you start from a random position, and from a random position, if you have high learning rate, you may jump to another random position, which is bad. So at first, you want to avoid too huge jumps, and that's why you use this warm-up theme. So it's very beneficial when you train transformers, for example, and large language models, this sort of stuff. And it doesn't hurt in other cases. So recommendation, again, is to use 5% warm-up by default. This is called cosine decay, because here it's linear, here it's like a cosinus. Yeah. And in terms of code, so it's actually very easy. You get your model somehow, you get your loss function, also known as criterion. And to define your gradient descent version, like SGD or full gradient descent, you call torch.optim. The name of your method, like NMW. In the first argument, you pass parameters, and then you pass like learning rate, weight decay, and some other arguments of your optimization algorithm. Here, there is a trick that you can for some parameters, you can define a special value. For example, here, it says that for all such parameters, use the default ones, and for all such parameters, use weight decay equal to 0. So the idea behind it was that, again, theoretically, for such parameters which are biases, it's bad to use weight decay. But again, in practice, I don't think many people do it. So that's theoretically how you should do it. In practice, you would probably wouldn't care, and you would just say that for all parameters, use this weight decay, learning rate, etc. Yeah.
I have a question about the optimizer. In the literature, is it known that for some optimizer, it's better to, for some tasks, it's better to use the optimizer than another?
So, in general, nowadays people use either Adam or Adam W, and that's all. They do not use any other optimizer because they are common and they were shown to work well in many different tasks. There are some new optimizers like Line from Google, etc., that pretend that they are better, but they are not popular enough to be used all the time. My Zoom died. Hopefully it will get better. Yeah, and sometimes when you read some papers which are probably older, you see that they use some other methods, or maybe some new ones also use some other methods. And if you want to re-implement their paper, it will be a good idea to use the same optimizer they used. So if they used a GD, use a GD. However, probably you would achieve the same or better performance if you still use Adam or Adam W. You will just need to change maybe learning rate, because learning rate for SGD might be a bit higher than learning rate for Adam, for example. Okay. Yeah. Yeah, so this is how you do cosine decay. Let's keep it for now. For scheduler, you just use torch.optim.alert scheduler and choose any scheduler you like. So here it's called lambda LR because we use a custom one, which is cosine decay with warmup. But there are some built-in ones like decrease learning rate by a factor of 2 every 1,000 steps. So it's called step LR, for example. Yeah, and finally, your training loop looks like as this. So for each iteration, you get your data, XY, you get your model output, which is output. You calculate your loss, which is a criterion between output and Y, so measure of similarity. You use loss.backward to calculate gradients, but calculating gradients doesn't update your weights. So it just calculates this delta L phi. To actually update your model, you need to call optimizer.step. So this would apply these gradients to update weights of your model. Scheduler.step will update the learning rate, and you want to zero all the gradients using optimizer zero grad, because otherwise, during your next iteration, you will accumulate gradients from the previous iteration. So if you want to delete this delta L calculated on a previous step, you need to call this zero grad. Otherwise, you would always sum delta L plus another delta L plus another delta L, and your model wouldn't train because you always accumulate gradients which are not actually corresponding to the current model, they were corresponding to the previous model. Okay? No, the forward step. So forward step is output equal model X, and this can also be yeah. So this is also part of forward step, where we calculate loss. Let's say calculating loss is something in between forward and backward. So forward is obtaining the output of your model given some input. Backward is calculating gradients and updating your model. So this is your forward, calculating loss, calculating backward gradients, and doing optimizer steps. This is your backward step. Are there any cases where you shouldn't use zero grad? So sometimes when you do not have enough memory to use large batch size, and you use a too small one, like let's say batch size of 1, it's probably too small batch, and you do not want to have this small batch size. So what you can do, you can say, let's use 32 iterations without optimizer.step and without optimizer.zeroGrad. Our gradients would accumulate for these 32 iterations, and only then we will call optimizer.step and optimizer.zeroGrad. So instead of calculating like average over 32 objects, we calculate 32 times average over 1 object and take the average over these 32 times. I don't know if it makes any sense for you, but that's when we can avoid, when we shouldn't use zeroGrad. So for this specific purpose, when we do not allow ourselves to have like such a huge batch size, we can only afford this small batch. Yeah.
Is it common to include in the loop clipping?
So yeah, you can clip gradient if you think that it should not be like larger than 1 or larger than 5 or larger than 10. But in the vanilla approach, you do not do this. You can do it if you know what you are doing and why you are doing it. For example, if you do not want again to do too large modifications, you can do loss.backwards, then clip the gradients, as you said, and then do optimizer step. Okay. Yes, so any questions? No, so I guess that's all in terms of theory for today. We have 12 minutes, and we have a seminar part, which I think will take 20 minutes. So if it's okay for you, we can cover it today too. Yeah, so this notebook is also published on GitHub. Yeah, we will work in PyTorch. So actually there are several frameworks like Keras, TensorFlow, JAX, but PyTorch is the one which people use the most today. So if you have like a new paper and it has open source implementation, most likely it will be Torch. One exception is Google. So Google uses its own thing, which is TensorFlow. Like you can also use TensorFlow, but it's just not popular these days. And yeah, so PyTorch allows you to create your model, to train your model, to work with your data, to evaluate and inference your deep neural networks. And also it allows you to do a lot of math-like operations like you could do in NumPy. So when you register to this thing, you saw probably in prerequisites that there is NumPy and you probably should know it. If not, I think you will still understand what is it. But if you already know NumPy, Torch, in terms of mathematical operations, is doing exactly the same thing. Like if you had like np.apps, you have torch.apps. You just replace np with torch, and operation is the same. Where can you get access to these notebooks? It should be on GitHub. Yeah, it's GitHub day 1. You need Jupyter, or you can use Google Colab, upload it to Google Colab or VS Code extension. I can send the information in the Discord channel or in the chat later. Yeah, so actually PyTorch is cool because it has very detailed documentation with a lot of examples and tutorials. You can go through them too. And they're very helpful for the beginners, and we advise you to have a look at them. For example, there is like a basics theme and a specific tutorial about how to train your first classifier, probably of either some images of numbers called MNIST, or of some like objects called cipher. So as usual, we just need to import our libraries like Torch, NumPy, for plotting, we import matplotlib. We do some hacks to make all the plots more prettier. This one is like HDR quality, let's say, and this one is to get a wide grid to also improve the image. And we want to create a tensor. So what is a tensor? So we have first of all, a vector. Vector is a one-dimensional thing, like number. Then we have matrix. Matrix is a two-dimensional thing, like you have rows and columns. So tensor is anything which looks exactly like matrix or vector, but with more than 2 dimensions. Like it can have like 3 dimensions, d1, d2, d3, and so on, dn. But for PyTorch, we do not discriminate between matrix, vectors, and tensors. We call everything as a tensor. So if it's a matrix, it's a 2-dimensional tensor, we say. Or if it's a vector, it's a 1-dimensional tensor. So d1 is like the size of your dimension, like how many elements you have inside this dimension. Let's say we have a vector of with 3 elements. So this is like the dimension number is, we have 1 dimension of size 3. Then if you have a matrix, like this, so we have 3, this is the size of the first dimension, but 4 size of the second dimension. So this is basically rows and columns. And if you had a third dimension like this, yeah, we could have like 1 number, this would be dimension of size 1, 2 numbers, it will be dimension of size 2, etc. So we want to create our first tensor. And we have 2 ways to do it. Either we use built-in functions like we did in NumPy, or we use NumPy objects or Python objects to create tensors from them. For example, we had a Python list like 1, 2, 3, and we can call torch.tensor with this object to create our tensor. And we see that the elements are the same, but now it's tensor and not just a list. The same thing when we have NumPy. Yeah, we had NumPy array, now we can have torch tensor from this NumPy array. Another thing we could use is from NumPy, which would give the same result, but could be a bit faster. Then we can use built-in methods. For example, if we want a vector of like 1, 2, 3, we can use as in NumPy the method called arrange. Note that we just change np to torch and got the same result. So if you already know how to create tensors in NumPy, let's say, you know how to do it in PyTorch. Basically, it's the same thing. And for each object, we can access some meta information, like what is the type of elements? Are they integers, floating points, or something else? For example, here we see that this is integer 64 bits. We can get the size, which is equivalent to tensor shape. Let's also print shape. But shape is, for calling size, you need these round brackets because this is a method. And for shape, you do not need these round brackets. But they return the same thing. So this is basically what are these dimension sizes for each dimension. Yeah. So if we have here vector with 1 dimension with 3 elements, this is a size 3. If we had like this 3, 4, tensor torch.shape would return, I guess, 4, 3 because it first looks at the rows and then at the columns. Okay. Yeah, and we can create multi-dimensional tensors. If, for example, we want tensor of this shape, we could use either a tuple or a list. And if we want all zeros, we would use torch.zeros. If we want all random using like standard normal distribution, we'd use rand n. And here are our tensors of the same size as we said them to be. Like the dimension of first size, the dimension the size of the first dimension is 3, the size of the second dimension is 2, etc. And we can modify the shape of our tensors. For example, we had a vector, and now we want to have a matrix. Let's say we had a vector of size 10, and now we want a matrix of size 2 and 5. So 2 rows, 5 columns. And we'll do tensor.reshape to 5. And we get our new reshaped tensor. We could use torch.reshape or torch.view. They do the same thing. The only difference is that reshape changes how tensor is saved inside your memory, while view doesn't do anything with your memory. So you can always use view, and if you get an error, you change it to reshape and everything works. That's a thing. You can always use reshape, but it's a bit more memory consuming, meaning that you do not probably want to do it all the time. Yeah, and one thing, sometimes if you did some operation like, let's say, permutation, we'll cover it maybe a bit later. Yeah, here then you would need to do reshape. I will talk about. So yeah, again, we could do like 3-dimensional tensor like this, and probably we want to do like a transposition in your matrix. Instead of having 4 rows and 3 columns, you want to swap it and have 3 rows and 4 columns. Yeah, to like make it like this. So this is called transpose when you only want to switch 2 dimensions, but it also allows you to switch multiple dimensions at the same time. For example, I want to put the first dimension at the last position and keep other dimensions the same. So I could call permute 1 to 0, and this moves stuff that was at the 0th position to the last position. Yeah, remind you that I will remind you that yeah, we index from 0, not from 1. Yeah, and we get yeah, if original shape was 2, 5, 10, after transpose we changed 10 and 5 in place, and here we moved 2 to the last dimension, so that's why shape changed like this. So the only thing to remember about reshape here and view is that you should be careful with permute operation, because it looks at how your tensor is located in memory, and if your tensor 3D is not a reshape, it's a view, there might be some bad things happening. So you can, if you don't understand what I'm talking about, just like whenever you use permute, think about and ask ChatGPT why you should use reshape, not view, and it will explain you why. And so is there a break? No, there won't be a break because we have like 10 minutes and then we'll finish. Hopefully. Should finish. Yeah, so we can add another dimension, like an imaginary one, using this operation called unsqueeze. So what is called imaginary dimension is this the dimension of size 1. So it doesn't actually add new information to your tensor, it just changes the shape. So if we imagine you had 2, 5, and now you have 2, 1, 5. Why would you need so? Because different layers expect you to have different input shape. For example, when you work with audio, you can have like batch number of audio sequences and each sequence of length t, let's say. But maybe you want to work with mono audio, meaning like left and right ear, or only one channel, yeah, or stereo when you have left ear and right ear. So this would actually add channel dimension here, like 2 for stereo and 1 for mono. And maybe if your audio is in mono, you would still want to have this imaginary dimension to explicitly show that this is a mono audio, not a stereo audio. Or more easily, like you have RGB images, like colored images, or you have a grayscale, black and white images. So black and white is image with only one channel, gray. And you can say that, okay, this is my gray black and white image, or I would add one imaginary dimension to say that I have one channel. So that's why when you use unsqueeze operations, something like this, you can use unsqueeze. You can use in NumPy like way with this none using slice. There's another way how you can do it. Is everything clear until now? Yeah. So when you have tensors, you can now do some operations like math. You can do summation. You can do multiplication, or you can calculate some statistics like what is the average value of elements of your tensor. Yeah, to do so, you do the same as in NumPy. You calculate the mean using dot mean, the sum using dot sum. You find the maximum using dot max, the minimum using dot min. Note that they have so-called dimension argument, which says, okay, I want to calculate average on not of all elements, but only over, for example, rows. So if I calculate average over rows, I would get 3 values for each column. While if I didn't use dimension, I would get only 1 value for the whole matrix as a whole. Okay. Yeah. And you can pass several dimensions. If you have like 3-dimensional tensor, you can take average over, let's say, dimension number 0 and number 2. You can calculate some linear algebra stuff like norm of your vector, or do matrix vector or matrix multiplication, or tensor multiplication. You have like matmul. You can do it with this @ sign, or you can do it as a method. You can do it as torch.function. They all return the same result, at least for the matrix case. You should be careful like what to choose. Just look at the documentation. But yeah, everything clear? Yeah. So until now, we could use NumPy for everything we did. Now we use torch automatic differentiation, which makes it so cool and so useful for the deep neural networks. So how it works? You need to create. So gradient is calculated automatically using computational graph. So you need some tensor for which you say requires grad equal true, meaning that torch should remember the computational graph that used this tensor to be able to calculate the gradient. By default, it's false, and you set it to true. Then you define some differentiable scalar function like loss is equal whatever given this input tensor A. And you request a backward pass using loss.backward. And the gradient will be available at a.grad. So you take .grad and you get your gradient. Let's look at the example. Yeah. And inside your computational graph, at least one tensor at the beginning as the input should have requires grad equal true, otherwise you will get an error. So, for example, we have x and y here, and we calculated this sort of operation, and we calculated backward. And notice that, yeah, we know the gradient here easily after just backward. So everything is working. However, there might be cases where you do not want to propagate gradient afterwards. We'll cover this in generative adversarial networks again next week. But how it works. For example, you want to calculate gradient for x, but you do not want to calculate gradient for y. First of all, you could, of course, say requires grad equal false here. But another way to do it is to say, let's say that y is y0.detach, meaning that we detach this y from our computational graph. It becomes like a separate element, and everything with what was before y0 is forgotten. So we forget all the computational graph that was connected to y0 before it actually became y. And if you now calculate the same thing, we'll see that gradient is set to none here. Yeah, so we are not calculating gradient for y. Yeah, and remember that we need to zero gradients, as I said, using this optimizer.zeroGrad, because otherwise the gradients would sum up. Let's say we have like x squared and 1 over x. These are their gradients. And if you do not reset, we will get 2x plus 1 minus 1 divided by x squared. Yeah, so if we do it like this, x squared loss 1x loss, we actually calculated 2x plus this stuff because we didn't zero our gradients here in between. Yeah, so here x grad is actually this gradient plus something we calculated before. To avoid this, we need to call 0 underscore to 0 gradient for this x, or optimizer.zeroGrad if we are using an optimizer. And now everything is calculated correctly. Yeah, so for memory saving, after you calculate backward, gradients are calculated. So during backward propagation, they're calculated for everything. But once the calculation is done, they are stored only for the final parameters that you want to optimize. Yeah, so if you have x here, which is called leaf variable, meaning that it's like the end of your computational graph, the leaf of your computational graph, you can access gradient for this argument. But for something in between, like y here or p, you cannot. And you will get a warning saying that you are trying to get a gradient of something which is not a leaf variable. And the thing is that, yeah, to avoid this, you can call retain grad to say PyTorch, hey, like save intermediate gradient for this variable too. And then it would work. Yeah, we requested PyTorch to save gradient for W, and now it works. Note that if you do not have any leaf variables that require gradient in your PyTorch computational graph, everything will fail. Yeah, you see requires grad false, so nothing actually requires gradient. So PyTorch doesn't know like what to calculate. He didn't save the computational graph and will return an error saying that, yeah, doesn't have a grad function, doesn't require grad. So at least something in your computational graph should have requires grad, at least one leaf variable should have requires grad equal true. So this will work, this will work. This won't work because we asked to retain grad, but we didn't have any leaf variables. So this W doesn't require grad. And this also won't work because we said retain gradient for X, while W is based on Z, not on X. So W actually also doesn't require gradient because Z is not requiring gradient, and we cannot calculate gradient for it. So you should be accurate with this sort of stuff. And of course, yeah, if you do Z requires grad equal true, this works. How much we have? It's close to the end. Is everything clear now? Yeah, so then one thing we had to have is data, like these pairs of input X and ground truth Y. So to do so, to have this in PyTorch, we have two objects. One is dataset, which basically says, like, given index in my dataset, return me a pair X and Y. Yeah, so let's say we have like x1, x2, x, etc., xn. Given Y, returns me xy, which is our ICE object. And data loader takes this data set and packs it into batches. Like we need to have a batch to calculate this batch gradient descent, stochastic gradient descent or Adam. And data loader takes batch size elements from your data set and combines them into one single large tensor. Okay. Yeah. So basically, yeah. So B is item 1, etc. item batch size. And to get these classes, you just call torch.utils.data and you import them like this. So dataset is a class. To create a dataset class for your data, you need to inherit from the main dataset class. So in Python, you have this like OOD, it's called object-oriented programming, OOP, I guess. So you need to define a class and say that this is a subclass of this main class dataset, meaning that it has all methods that are defined for this parent class, but we can override some methods for our case. For example, we need to override init, where we define some useful we give some useful information to our data, like the actual data set, like these pairs of X and Y. We need to define get item, which says how to return item number, so how to return XY given I. Yeah, so how to return ith object of your data set. For example, here is self.data index, because data is just like a big tensor here, and we can offsize like. So here it will be something like D, like let's say N. Yeah, and when we take data index, we take like the ith row and get a vector of size N, something like this. Yeah, and we need to define the length of our data set, which is just the length of this self data here. And let's say our example data set is just like 1,000 random elements of size, random vectors of size 10. We just create this data set as this, and if we take 10th element, we'll get our 10th vector like this, x10. And the length of our data set is 1,000 because we created 1,000 vectors. So data loader will use this data set to split it into batches, and it will say, okay, let's use 20 random vectors from our data set and combine them into one huge matrix. To call data loader, we do something like this. We pass the data set and define the batch size. We can say whether we want a random or non-random version by saying like shuffle equal true, which is default, or false if we do not want to shuffle. For example, we do not want to shuffle test data probably because we do not care, but for training data we care. And there is another thing, but we'll cover it tomorrow, which we can pass here. And then we just iterate over this data loader, because this is an iterator. Like when we iterate over it, it returns us like the first batch, then the second batch, then the third batch, etc. And we can get the first batch like this, and we see that it is of the proper shape. Or we can use islice or next to just get like the first batch, something like this. Yeah, so here batch is a tensor, and our dataset returns only X. So if we had like Y, for example, if we would have something like self labels, we could return something like this. And this would be like then the output of data loader wouldn't be a tensor, it would be a tuple of tensors, a pair of tensors, one for X and one for Y, for the ground truth, for the labels. Clear? Clear. Yeah, and the final thing, I'm sorry that we are late. That's hopefully the last day we are late just because we started later. Yeah, so how to do actual optimization? we need to define our function, let's say like f, that does the forward step. Let's say it's like this. And we need to calculate the loss, which is here, let's say f at x itself, because we want to find maybe the local minima or the global minima of this squared function. So we do one step of gradient descent using torch.optim.sgd with some learning rate, also known as step size. And we change this starting x to a new updated value that we obtained using our optimizer. And we repeat this num-step times to update iteratively our approximation. So this is our f, this is our minimal, and we would start, for example, somewhere here, and we would want to update our starting position using gradient descent to actually get here. Is it clear, the setup? Yeah. So what we do, we start with a random value, let's say like this. We initialize a random vector, and we initialize torch.optim, let's say .sgd. In the first argument, we pass what we want to optimize. We want to optimize our current solution. And we pass the learning rate, let's say 1e minus 2. And let's say we want to do it for 200 iterations. Then we say that our loss is this function. We do zero grad to zero the gradients, as we discussed. We calculate backwards to calculate the gradients. We calculate optimizer.step to update our solution. And here is just some stuff to visualize what is going on. And you see how this star iteratively goes down and down to reach this local minima here. Is it clear how it works? So when you have a deep neural network, it's exactly the same loop. So like this for simple function like this blue one, but instead of this squared function, you will have like a complicated deep neural network. Everything else is the same. And it won't have like one parameter xs, it will have many different parameters. And you will exactly the same optimize your solution to get to the minimal position. Yeah, so again, general pipeline, you define your model, you define your data set and your data loader, then you choose an optimizer. It can be like SGD, it can be Adam W. We recommend Adam W. You define your scheduler like Casal and annealing or one cycle LR or like step LR, something like this. Again, we recommend Casal and annealing that we covered during the lecture. And then you iterate over your data loader, over your batches. And for each batch, you calculate the loss, do backward, run optimizer.step to update the weights, and scheduler.step to update learning rates. And you try to avoid forgetting about zero ingredients. And that's all your model is trained. Yeah, this choice of the scheduler, etc., you will use just recommended or use the ones which you are used in the paper you are trying to implement, or inside the domain you use. But if you use Adam W and Casal annealing with Walmart, you probably are doing pretty well. Yeah, if you're trying to re-implement the paper, a good idea would be to use the same setup as they have, but probably using Adam W with Casal annealing would be as good as, or even better than using the paper setup. And that's all for today. Sorry that I took 20 more minutes. Hope this is all right. Thank you for coming today.